Brilliant. Well, welcome to the first Ice and Snow session of FRINGE 2023. So Thomas and I are delighted to be chairing this session, and we've got a brilliant lineup of speakers. First up is Thomas Nagler, and he's going to be delivering a presentation on looking at ice velocity and discharge from ice sheets using complementary C and L band SAR datasets. So take it away, Thomas.
Okay, thank you, Anna, for this introduction. In this presentation, I give you an update on what we achieved in the last 3 years on monitoring ice velocity and discharge using Sentinel data, but also other datasets. And I give you also a kind of overview on the recent developments and what we are just working on. Now, currently, Sentinel-1 was a game changer, actually, in monitoring polar ice sheets, and this is what we are doing currently, continuously since 2015 onwards, first with Sentinel-1A only, then including also Sentinel-1B. Later on, with the end of 21, we managed, or we had this failure of Sentinel-1B and had only one Sentinel-1 data, and we were looking for other data sets and satellite data in order to jump in. So what we are continuously monitoring in various ESA projects, but also Copernicus services, are the big ice sheets in Greenland and Antarctica. Additionally, also on the Northern Hemisphere, we are looking for Canadian Arctic ice caps, Franz Josef Land, Russian Arctic, but also including Iceland. And on the Southern Hemisphere, we are looking not only to Antarctica, but also to South Georgia, and on the glacier applications also to Patagonia. All the acquired data sets from Sentinel-1 are actually processed for these data sets, and the data sets are available on various geoportals in order to download, and they are used by a couple of scientists. Now, one example for Antarctica, what we are providing. For Antarctica, we had one campaign data with full coverage. This was in 2016, full coverage without the polar gap. Since then, we are continuously monitoring all the margins. This was within the capacity of the satellite data of Sentinel-1A and B. And together with Pierre and later Nuno, we actually managed to establish a kind of acquisition strategy to have at least one look direction for all the margins. So 99% of the margins are actually covered, and this, of course, helps us to estimate the ice discharge. We are producing monthly products starting in 2015, and they are updated on an annual basis. The method is a standard method combining coherent and incoherent offset tracking. We are providing easting and northing velocity components, but also the elevation change when we are looking to the displacements of the image acquisitions. And for each of the pixels, we have an uncertainty estimates. The product is posted in 200-meter pixel spacing, and especially for Antarctica, in contrast to Greenland and other ice caps, we have to apply another processing steps, which is probably not that much known. So especially for the floating ice, we have some tidal effects which are going up and down, and therefore this has an impact, of course, on the ice velocity, and we established a method actually in order to correct for this tidal motion, which has an impact only on the slant range displacement. For this, we are combining a tide model, the CATS 2008 model, which is projected, which is actually calculated for the acquisition dates when we are combining the SAR images, and this is projected towards the line of sight directions, and then we get the displacement and can correct actually this for the tidal motion. Additionally, we are also correcting for the barometric effect. Just to give you some ideas how big these vertical displacements are for the tides, it depends on where we are on the ice shelves. This is 1 to 2 meters, but can be also up to 6 meters in difference, depending also when the images are acquired. The inverted barometric effect is much smaller, it's in the range of a few centimeters only. One critical issue is, of course, the transition from the grounded ice towards the floating ice. And here we are modeling this with a elastic beam model, and the length of this elastic beam we are estimating from the grounding line fringes taken from the regions, and this is interpolated along the margins. Just to give you an example here, for one of the glaciers, the flow lines for different dates, we see here in the purple line, this is the average, multi-year average of the ice velocity, and all this spreading here is caused by the different tidal motion. And applying actually this correction, we are more or less widely correcting for this effect. There is still some residuals in this, which is the inaccuracy in the CATS model, and maybe this method can also contribute in order to improve the tidal models. Now, the next step, what we did is a kind of switching from offset tracking towards SAR interferometry, and in 2020, 2021, this winter period for 3.5 months, we arranged with ESA together to have an acquisition strategy to get ascending and descending images all over the Greenland ice sheet, almost a full coverage, and for each of the repeat tracks we had about 4 continuous acquisitions at least, or more. And together with DTU, we managed also to correct for the phase jumps along the bursts which are appearing when we have ice motion in azimuth direction. And finally, we were coming up with a product, what we have seen like this. It has a much higher resolution. It's 50-meter resolution, and just combining crossing orbits in ascending and descending direction. But still, what are the problems with this product alone? We see here that we still have, although this was a special campaign, we managed, we have some gaps. Additionally, we have some gaps along the fast-moving glaciers, which are shown here in gray. So SAR interferometry cannot provide any information there at C-band because of the fast motion within the 6 days period, and also due to the sharing. And therefore, we are additionally calculating the SAR interferometry with the flow direction from the multi-annual offset tracking method. This helps us in order to at least fill some of the gaps where we only have one look direction. The second component of the velocity is coming from the flow direction, from the multi-annual. And of course, we have the assumption here that over this time period, the flow direction is not changing, which is probably the truth for the interior of the ice sheet. This approach does not provide any solution of the ice divide itself, and does not solve the problem of the fast-moving glaciers on the western side, for example, of Greenland, like here, they are still gray. Now, therefore, we are combining this together with the offset tracking in order to fill the fast-moving parts, and this is now this advanced high-resolution IV product combining all the different techniques. We are filling the gaps where we have only one observation direction given using the flow direction, and for the very fast-moving part, we are using the offset tracking. And of course, we have a priority in the merging. The highest priority has, of course, the crossing orbits ascending descending solution, because this is the highest accuracy. Now, just to show you a kind of profile across the ice divide, in blue color you see the offset tracking solution, which is still noisy. There are still some ionospheric strikes included. Then we have the 2 interferometric approaches, and when we combine it, we see very nicely this greenish line where we have almost zero motion at the ice divide. We validated this with one special GPS data set, which was acquired by Christine Hilbert from the Danish University, and these are published GPS data in a small part of the region on the Negis ice stream, and we see a very good agreement between the INSAR solution and the GPS data, which agrees quite well. So in the mean, it's a millimeter per day difference or less. Now, what are the requirements for such a part? So we need a systematic coverage for ascending and descending passes. This was done only for Greenland for this winter period 2020 21. It was also planned to improve it for the next season, 21 and 22. But unfortunately, Sentinel-1B failed, and this campaign was cancelled. And then, of course, we had only 12 days repeat pass data available, and this has a reduced coherence. And therefore, we are waiting really that Sentinel-1C is coming up very soon, in a couple of months, and in order to fill this gap. But in the meantime, we are also looking for other opportunities, and then we found actually the opportunity for SAOCOM L-band SAR data. So those who are not familiar with SAOCOM is an L-band mission which is operated by KONE together with ASI and has a background mission over the ice sheets. It is operating in strip map and TOPSAR mode. TOPSAR mode, I have to say, we did not process because the bursts are not synchronized. So we had to focus only on the strip map in order to get interferometry working. And you see here on the side the acquisitions coverage for Greenland and the Antarctic Peninsula. Other parts of the Antarctic are not covered, with 8 days using SAOCOM A and B, which were launched in 18 and 2020, and also 16 days with one satellite data only. And we were selecting now a couple of examples which I want to show the progress in order in combining SAOCOM data with Sentinel-1 data. And here actually I want to look towards the Antarctic Peninsula, where we have only one descending acquisition from Sentinel-1 and with the different tracks, but this is continuously acquired since 2015. And we have the opposite ascending direction from SAOCOM as it is shown here in this one. Unfortunately, when we look to the coverage of the 8 days, which is of very high relevance because this is in preparation also of ROSE-L, which can provide the 6 days repeat observation, so very similar to the 8 days pairs of SAOCOM. The coverage is not that good, we have to say. So there is no systematic planned acquisitions done by KONE in this region. So it's a kind of background mission what they are operating here. Now the first example, I show you how the interferograms look like. So I select now a region in the very south of the peninsula. You see here the tracks of Sentinel-1 with the line of sight direction from here to here, and SAOCOM strip map mode, much smaller, only 66 kilometers wide, with the look direction from the bottom to the top. And this is a relatively fast-moving glacier in the upper part, in this region here, with about 1 to 2 meters per day velocity. We have a tributary in the south of it, which is flowing into this glacier, which is much lower in the velocity, about 10, 15, 20 centimeters per day. Now this is the velocity magnitude derived from the overall 7 years offset tracking solution. When we look now to an interferogram of this region, we see that we have coherence over 6 days, which is really nicely working. But we have also a couple of challenging issues which prevents this to apply over a 6-day periods C-band data directly. And this is especially when we are looking to the sharing zones in this region or in this region. We are losing here the fringes because the fringe frequency is too high. And also in the faster moving parts upwards the glacier here, we don't get any fringes actually. So a solution would be to operate 1C with a 1-day time delay, like we had it during the ERS tandem mission, but obviously this is not possible. And we are actually using SAOCOM data. First, the 24 days repeat cycle image looks, the look direction is now different as from Sentinel-1, it's from the bottom to the top, but we still have very good fringes, but the same problem actually as we had for Sentinel-1. We are losing in the sharing zones the coherence and cannot resolve actually the fringes, and this causes problems in unwrapping. Also in the inflow of the small tributary here, we have this issue. When we are going actually to 16 days, so this is a little bit longer than what we expect from NISAR with 12 days repeat cycles, but it can be somehow compared, so NISA will be a little bit better. We still have some issues in these problems. What works very nicely is, of course, the 8 days. So 8 days is very similar to ROSE-L. ROSE-L will have a 6 days repeat cycle, will be improved much better, and that's, of course, when we look from the phase unwrapping point perspective, quite nicely. Now, one example for a slow moving part. We are moving now towards just north of the Antarctic Circle to the Jason Peninsula. Jason Peninsula is dividing the Larsen C ice shelf and the Larsen B ice shelf from on the left and on the right side. And small tributary glaciers are actually running into these Scar Inlet, Stratton Inlet, and Adie Inlet. On the very right side, you see the Leopard Glacier. So this is a big glacier actually feeding the fast-moving part of the Scar Inlet. Now, this is the overall ice velocity map from offset tracking. You see very nicely that we have already observed some of the ice divide on the Jason Peninsula. And what we see already are some shown here in light blue, the smaller tributaries which are slowly moving. So these are visible in this image. Now, when we go to one pair only, we have still ionospheric effects in there and other issues caused by bonds. So this is 6 days Sentinel-1 pair. SAOCOM 16 days, so 8 days were not available. Offset tracking works also quite nicely. We get the main picture of the offset tracking. When we're looking to the interferograms, 6 days, we see that the fringes are very well developed. We are recognizing very nicely the grounding zone and the grounding line, which helps us actually to delineate the floating ice from the grounded ice. But on the fast-moving ice sheet, we are actually missing the fringes. So here, the fringe frequency is definitely too high, so it cannot be unwrapped. For the Alpine, this looks much better. We are getting more or less very good coherence. Also in the fast-moving parts, we are getting fringes where we can rely on this. And finally, we are combining this. We were able to unwrap these images, and we can combine the Sentinel-1 and the SAOCOM INSARP crossing orbits. And for the floating part, we are already applying the tide model, in order to correct for the tides. We have here a problem, of course, in the sharing zones. When we are moving from the slow-moving part towards the fast-moving part, because here, as we have seen before, we have no coherence in the Sentinel-1 image, and therefore this is masked out because we cannot get a solution. When we are showing here the combination of crossing orbits and tide corrected of Sentinel-1 and SAOCOM, together with the SAOCOM INSAR only, including the flow direction solution, then we are getting more or less a complete picture. And then, of course, we have a very nice solution for that. We can, okay. Okay. Then we have here a cross profile. We see that in red line across the ice divide from the floating part from Larsen B to Larsen C, actually, we see that the INSAR solution is much more quiet and then actually the overall SAOCOM Sentinel-1 offset tracking solution. One more example to the discharge, zoom in now to this area. This is the Sentinel-1 offset tracking solution, and as I have mentioned before, we see in some places this in light blue, the faster moving parts. When we are going actually to the INSAR solution, we see much more detail on these slow moving parts, so the sharing zones are much sharper in this case. And what we also see is that the grounding line can be refined based on just this image, because we see very nicely the border between the bluish color and this cyan to greenish color. So here we can probably provide more detail. Then we can actually, what has the impact on this? When we are looking, for example, to one of the drainage gates on Adie Inlet, using the both velocity solutions, we see that the impact on the ice discharge, just due to this better knowledge of the ice velocity, already has a 10% change in the ice discharge for this very small part. Although it's very slow moving, it has a big impact on, because there are large parts in Antarctica which are, where the ice discharge is caused by slow moving ice. And when we apply this, so what is the vision when we are looking here, for example, to Greenland and some of the glaciers, then we see here that especially on the sharing zones, we have these steps in the offset tracking product. Using the proposed solution of Sentinel-1 INSAR together with SAOCOM, we could probably improve this to get this more smooth and improve also the ice discharge estimation. And then, of course, what we actually expect by the improved ice velocity, just improving this with a higher resolution and a better knowledge, we can probably bring down the uncertainty in the ice discharge. But another problem is here that we have also a bigger uncertainty also in the ice thickness. So we need actually an improvement also in the ice thickness data in order to get this done. Now, to the conclusion, so this study shows that we have a major improvement in the ice velocity using synergy of C and L band INSAR. So this was demonstrated with Sentinel-1 and SAOCOM data. The L band actually is really very, very helpful and covers regions which are decorrelating in C band and being less affected by the decorrelation, especially when we have strong velocity gradients due to the reduced spring frequency, and this enables or supports also the phase unwrapping problem. L-band is more sensitive to disturbances by the ionosphere, and we have to correct it. This was not done in this case. We processed a couple of images and took this one, which has the less ionospheric effects, but we have to work on that. So there is still some solution needed. SAOCOM has a smaller bandwidth, and therefore we have to look what is possible. L and C-band SAOCOM Sentinel-1 combinations provides a smoother ice velocity field with a wide range of velocity magnitudes. And this also is dedicated to monitor the smaller and slower moving tributaries to the ice shelves in great detail. And this leads to a better estimation of the accurate discharge. And why are we doing this? We are looking forward for Roselle, of course. Roselle will be a 6 days dual satellite mission, which will come in a couple of years. And very close to this, we will have NISAR, and of course, NISAR is covering Antarctica from the full part, and we can use both satellites together in order to improve the estimate of the ice velocity. Thank you.
Fantastic, thanks very much, Thomas. Great presentation. If running slightly over schedule, so we're starting off a little bit late, but let's have one question from the audience. We've got a question up there. Thanks, Jacob. The mountain running up the back of this conference has already started.
Nice presentation. About SAOCOM, which type of data do you use? Is it strip map or TOPS?
No, we used strip map, only strip map. We tried TOPS data, and there are a lot of TOPS data acquired, but for interferometry, what we learned is that the bursts are not synchronized, and that's the main issue. So, and therefore we tried it, we checked our software and so on. We really got a little bit obsessed, but then we heard that those data we actually tested were not burst synchronized, and this is, of course, would be very good because there's a very lot of TOPS mode data acquired, but we were focusing now on strip map.
Okay, thank you.
And Irina, yeah, you're right behind, so there you go. Breaking all the rules.
I was coming a little bit late, sorry, but probably you have mentioned. Did you had some studies about the different propagation into the snow, depending on C and L band, and the difference in velocity that you potentially can observe?
Yes, so in principle, this was not included here. We were looking into this. But what is definitely needed are also some field data in order to prove this, because that's somehow a kind of guessing. But of course, what we have is we are assuming that in the top meters for Antarctica, the ice velocity is not changing. And if the conditions are the same within 8 days, which we can assume during the winter period, then of course the phase center is always more or less in the same layer of the ice. So we are not, of course, if there's a change, for example, melt or whatever, you might get even at L-band some coherence, and then the phase center is jumping up. But this we excluded by selecting the right data.
Fantastic, thanks very much. And I've written a note about that so we can come back to it in the roundtable discussion later, because we might make a recommendation to do that work with Expand as well later. Brilliant. Okay, thanks very much, Thomas. So next up, Bernd, you're already ready to go if you'd like to come up to the stage. So Bernd from the University of California, Irvine is going to give a presentation titled Towards a Multi-Frequency Virtual SAR Constellation for Grounding Line Measurements. So thank you very much.
Thank you very much. My talk is about work that's not by me, but by a group of people. Some of them are acknowledged as co-authors. I mentioned Eric Rignot, the group lead. Enrico Sirazzi, he's a recent postdoc in our group. Hanning Chen is a PhD student, and Pietro Milillo is a former colleague who is now with the University of Houston. I also want to take this opportunity to mention one unnamed co-author of our work, and this is Jeremy Mougineau, because it's coming up on about 1 year that we lost Jeremy, and this community lost a huge talent, and I'm talking about the cryosphere community as well as the remote sensing community. If you haven't heard the name, I encourage you to look up Jeremy's publication record. You can learn a thing or two. And his legacy will live on through upcoming missions and also the past work that he's done. But to move forward, like the Ice Sheet CCI, NASA also funds some groups to produce geoinformation products for the ice sheets. Our group in particular is funded to produce products for the Antarctic ice sheet. And we have ice velocity products, grounding line. We also have the bed, which is a level 4 product that includes modeling, and ice sheet boundaries. Our approach is to use all data sets that we can get our hands on. And we have started this project in 2009, so we have been blessed with a long-term funding envelope, and we just recently got awarded another round of funding for this work. But I will not focus too much on ice velocity. My talk is about grounding line, and also the title said virtual constellation, and one of the first questions that I had this morning when I uploaded the presentation is, what does a virtual constellation entail? What does it mean? And it's about coordination of systems that are not related to each other, where in talks this morning we heard about system of systems, where ESA has the privilege to design multiple missions that are interlinked, coordinated, and work with each other. Well, there is also the opportunity to talk about space missions that are built without sort of consideration of one another, but could be used with some sort of level of coordination. And the International Polar Year was one of the first events where space agencies got together to prepare for supporting this effort, this research effort, and this was in 2007. And of that coordination was born the Polar Space Task Group, which continued for a number of years after that, where space agencies got together, invited scientists to do some science coordination, write requirements, documents, and identify observation gaps that are persisting with current observation plans, and then hopefully look into who can contribute with what mission to fill those gaps. And this was a time when, before Sentinel-1, so it was a different period where acquisitions were still made on campaign mode. But some of the huge successes of PSDG were sort of the first continuous pole-to-coast Antarctic velocity map, and that's sort of produced by our group, but wouldn't have been possible without the coordination from the various space agencies. And the slide also lists some other aspects. This was support of polar science, so it was sea ice, ice sheets, also snow and permafrost. A more recent effort to do coordination is a much broader effort. That's the International Coordination Group for SAR missions. The group has been meeting a number of times now, but it's much broader, and it also goes much deeper into sort of data formats and also sort of literal mission coordination. But one of the outcomes of a recent meeting was that PSDG constitutes a successful example of how such a science-led coordination can be organized, and they also encourage PSDG to be re-established. Sort of the effort went into a bit of a hiatus based on a leadership change at WMO, which caused sort of the coordination efforts to cease to some degree, and also the success of Sentinel-1 sort of meant that we had a baseline mission that ensured continuous observations. But I want to move to grounding line. Thomas already mentioned this is the location where ice detaches from the ground and starts to float. The position of the grounding line is not static. It's also a measure in terms of whether or not the glacier is stable or retreating or advancing. The latter is sort of more unlikely these days. And we can use the vertical displacement, sort of the tidal displacement, to measure the position of the grounding line using SAR interferometry. So having 2 interferograms, we have 4 tide states, and we use the differential tide to make this measurement. And the name of this conference is Program, so I should show at least one fringe pattern. The dense fringe pattern here is the differential, the flexure of the ice shelf of the ice based on the differential tide. And we produced a continent-wide grounding line product. The lower row shows this divided by sensor as well as divided by year. And the upper row has Sentinel-1, where at first I started doing the sort of best of double difference interferogram to draw a single grounding line, but then moved pretty quickly into trying to get all available grounding lines for a number of years. So in the past we had campaigns, so we had only a single grounding line measurements or maybe a handful. With Sentinel we started to getting ongoing acquisition campaigns, and so measuring multiple grounding lines. And we started to seeing short-term changes that were sort of what we still think is caused by tidal modulations, that the grounding line moves back and forward based on the tide. And Thomas mentioned the term grounding zone, and I think the community needs to come to terms in terms of, we define the grounding zone as this upstream, downstream boundary of the short-term motion of the grounding line. And the period that we decided was a 1-year period, but we can, with denser observation, as I will show in a bit, measure that grounding zone also in a shorter period of time. So we define the grounding zone product that constitutes this upstream and downstream boundary of the short-term migration of the grounding line. And some of our research shows that the grounding zone is hugely important because seawater can access this at least partially, and the water transport is enhanced because of incoming and outgoing tides. So we have heat transport that encourages subglacial melt in this region. So one aspect to measure grounding lines for fast glaciers is to use short repeat expand data, and our colleague Pietro Milillo has been using Cosmos SkyMed that has that capability about every 16 days and has published a number of papers. Our colleague Virginia Brancato, who is now with JPL, did this for Denman Glacier. And the region that's observed here is one of the more critical regions, so the Amundsen Sea embayment containing Pine Island, Thwaites, as well as Pope Smith and Kola glaciers. One aspect that I'm really excited about is we had a recent opportunity to look at RADARSAT constellation mission data. CSA used to not plan acquisitions in the Southern Hemisphere originally, but the loss of Sentinel-1B sort of tragedy also led to some opportunity because ESA asked for support in the Southern Hemisphere for sea ice monitoring, and that opened the window for some example acquisitions or test acquisitions over ice sheets. And we had a plan ready to go to make suggestions for areas over fast glaciers. And here are some examples that show that the 4-day, 5-meter interferograms are just really astonishing and provide information that augment the information provided by Sentinel-1, which fails to produce a grounding line signal, especially now with the 12-day scenario. But even 6 days is challenging for some of the fast glaciers. So we envision RCM to be an excellent mission to augment Sentinel-1B with a handful of acquisitions or acquisitions in a handful of regions that have continent-wide impact on the science. The other aspect with short-term X-band interferometry is ICE-Eye. It's a commercial mission. The mission has a capability to collect 1-day repeat data on a short-term basis, but ongoing, so there is no window in between. And we had 2 acquisition campaigns on Petermann Glacier. This is in Greenland. One in 2021, that's October, and the other one in 22, that's May. And there were 9 consecutive days, which led to a lot of possible combinations, and therefore also a definition of the grounding zone, which is identified in black. We also looked at L-band data. One of the advantages, but also a challenge, is the reduced sensitivity to displacement in terms of the number of fringes is fewer. With ALOS 2 in particular, we ran into the issue that the 14-day repeat cycle sort of coincides with the tidal frequency, and so we got a 0 differential tide more often than we cared for. But the results that worked show that L-band is an incredibly useful resource. JAXA has difficulty disseminating strip map data. Fortunately, I had the opportunity to work on a PI science program, and they had acquisitions of opportunity over a number of test sites in Antarctica. But it's not a sort of ongoing observation plan, so some of the double differences that I show here are ones that I would not necessarily use. For example, the April and October interferogram in the bottom right is something that I would not normally choose to do. We would want a shorter period for the double difference. Thomas also mentioned NISAR as an upcoming L-band mission. The acquisition plan is very generous for Antarctica. This is a left-looking mission, and we have high-resolution coverage over coastal Antarctica and slightly lower resolution in the interior, but we have ascending and descending coverage every 12 days. So from an ice velocity point of view, this is very promising. The grounding line coverage should also be very generous for this mission, but we expect sort of complications in fast-moving glaciers also due to the 12-day repeat. To summarize, these acquisition plans the missions are not formally coordinated, but our recommendations for acquisition plans are based on results and experiences during the Polar Space Stars Group science coordination work, as well as on our results from our measures project. I want to say that no single mission to date and also no upcoming mission that I can foresee is capable of providing the information content that matches this virtual constellation. Coordination also allows us to use the assets responsibly. For example, for RCM, we know there is not going to be a continent-wide coverage, but with a handful of test sites, we can achieve continent-wide science impact. Sentinel-1 provides a crucial baseline data set for grounding line measurements. The primary coverage motivator is ice velocity, so grounding line is a nice add-on because we have the coastal coverage right there. RCM is a great mission to augment Sentinel-1. We both are X-band missions. So the primary motivator for our recommendation was, in this case, the grounding line or grounding zone measurements. NASA also has sort of a motivated coverage by ice velocity, but grounding line is definitely an aspect that we will be looking at. We do expect decorrelation over some fast glaciers. So to date, we are unable to reliably monitor key critical glaciers. In this case, the Amundsen Sea Embayment, Pine Island Glacier, and Thwaites Glacier still pose a challenge. It has been shown that Cosmos SkyMet has one-day capability, which is useful, but that data set is not sort of openly available. ISI is a possible candidate. We have experimental one-day repeat time series that has shown was successfully collected, and we have shown that this is a really useful data set for grounding line or grounding zone measurements. This is a commercial data set, however, so it would need agency support in form of a third-party mission or a sort of commercial purchase by the agency to then make the data more publicly available. And with that, I also want to say that our group is looking for a postdoctoral candidate. If you're interested in this offer, then please scan the QR code for more information. And this is the pole to coast ice velocity map that I mentioned. That's similar to the map that Thomas showed, was based largely on the INSAR phase, but it took 5 years to get there, and in actuality we used data collected over 20 years. With NISAR, the collection of ascending, descending will be sort of every 12 days, so there should be exciting times ahead. Thank you.
Thanks very much, Bernd. Great presentation. Have we got a question from the audience? Yeah, in the middle.
Yeah, I have 2 short questions about these ISAT images. First is, do you know what acquisition mode was it? And the second would be like if you have been successfully being able to process them and co-register them and so on, because as far as I know, these nanosatellites can also sometimes have this orbit inaccuracies and so on.
Sorry, can you repeat the first question, please?
What acquisition mode are these ISA images? Is it street map or spotlight? ISA, yeah, sorry.
Oh, it's strip map data. Strip map.
And have you been able to properly make use of them? Because sometimes...
ISI, what we have been approached by the company, and they wanted some input on glaciology results for an Antarctic glacier, and I said, well, you know, we do work in Antarctica and Greenland, so we came to an agreement to make some Greenland acquisitions. What we need for grounding line measurement is a next neighbor baseline, and that's what they can do. So they can maintain a baseline for the next acquisition, but the baseline is obviously drifting over time. So there is not, right now, as far as I'm aware, they don't have the capability to collect long time series that have a baseline that sort of fits in a tube. So those baselines are drifting out, but we are only looking at the next neighbor. And so their capabilities right now fit exactly with what we need. So we were able to use that that capability that ISI currently provides, but I think going forward they will develop further capabilities.
Okay, thank you.
And you had a second question? I don't know.
Okay. Just in the interest of time, we'll take that one offline.
Okay.
But thank you very much. Great question, and thanks very much, Ben, for that brilliant presentation. So, Thomas.
Oh, thanks, Anna. The next presentation is given by Benjamin James Wallace from University of Leeds. It will be on a new methodology for ice shelf and glacier grounding line delineation with SAR in low coherence regions using tidal motion correlation. Please, Ben.
Yeah, hi. Thanks, everyone. And I feel like I'm in trouble now because I've been introduced with my middle name. Only my mum does that normally. So hi, I'm a PhD student here at Leeds. I'm in my final year now, and I'm going to talk to you about some work that started more as a frustration, that then turned into an idea, that then turned into a side project, that then turned into a significant piece of work. And I'm slightly a fraud here, because this is about what to do when you don't have any coherence and you can't make interferograms, but you want to study the grounding line. So, as I said, this is from my PhD, which has basically been entirely studying the Antarctic Peninsula, which is this sticky out bit of Antarctica. Do I have a? Oh, yeah, great. So the peninsula is really interesting because it's got everything that makes glaciology interesting to me. So there's fast glaciers, there's ice shelves, there's two completely different oceans on either side. And it's a really important region because although it's small, it's contributed about 19% of Antarctica's ice mass loss in the remote sensing era. So for such a small area, it actually really matters. And we've seen massive changes in the cryosphere here, so ice shelf collapses, retreats and accelerations, and more recently, some work that I've done in my PhD, looking at seasonal speed trends on the peninsula. We've been able to observe these with Sentinel-1. It shows how sensitive this region is to the climate on short-term timescales. And this is, in many ways, a place where we can study some processes in Antarctica that don't happen elsewhere. So ice shelf collapse, seasonal speed trends. In some ways, it's like our future for Antarctica, perhaps. It's wetter, it's warmer, there's more melt. So this talks also about grounding lines, and this has been planned very well because Thomas talked about the peninsula, and Bern talked about grounding lines, so I can whiz through some of this. But broadly, the grounding line is where the ice starts to float. It's more of a, as some people say, zone. Perhaps that terminology is a bit confused sometimes. But the reason it's important is that if we want to measure ice discharge and ice mass loss, we need to know the position of the grounding line. So for ice discharge measurements, but also for interpreting altimetry. And any ice sheet model, particularly models that are looking to project the future mass change of Antarctica, need accurate grounding lines to initialize those models. That's becoming increasingly important as ice-ocean coupled models are starting to be a major focus of research. If you don't know where the ice and the ocean are coupled, then that makes it more difficult. And again, these can tell us about stability as well. So when you study the peninsula a lot, you realize quite quickly that a lot of the grounding lines that exist, measurements that were made there, they're out of date. The reason for this is that it's probably one of the worst places for coherence in Antarctica. It snows a lot, it melts a lot, flow is fast, there's lots of tiny glaciers, and there's a radar shadow, all sorts of issues. Apart from outside the major ice shelves, a lot of the grounding line measurements we have are from the tandem phase of ERS 1 and 2, which is in 1996, which I was alive then, I had been born, but I don't think I could say synthetic aperture radar. So this creates a lot of difficulties interpreting measurements, and that hasn't worked very well, is it? On this screen. Anyway, a good example of this is a paper that came out in 2019 by some of our colleagues at Leeds were on it, and a friend of mine, Pete Tuckett, and that created quite a lot of discussion in the community, particularly around interpreting drainages of superglacial lakes, and there was a discussion about if the grounding line data is out of date, how can you know what you're looking at is floating ice or grounded ice? And there was a bit of back and forth about that, and I don't kind of want to get into it too much, but the point of telling that story is that in many ways on the peninsula, a lack of grounding line information is a limiting factor in our understanding of the processes that are going on here and being able to do science in the peninsula region. So in my PhD, I quite often went, it'd be really nice if if someone would make a new grounding line data set for the peninsula. Wouldn't it be good if we had updated grounding lines? It became increasingly apparent that maybe I might have to be the person that would do that if I wanted it. So there's a few methods that you can use where you've got low coherence for looking at grounding lines. There's a method called differential range offset tracking, which uses feature tracking to look at vertical motion. And that does work, but it's less sensitive than INSAR. It requires manual delineation still. You can use repeat altimetry, and that works really nicely close to the pole, but at mid-latitudes or lower latitudes like the peninsula, track spacings for altimeters are the widest. They get wider as you go away from the pole. So it's really hard to resolve small features there using repeat altimetry. And you can also use static methods like looking at surface slope, but that's not a dynamic measurement of the tidal motion. It can be hard to interpret as well where there's ice planes. So these are all kind of unsatisfying in a number of ways. So I was thinking about this and I realized we actually kind of, like my dad's shed, there's a lot of useful stuff lying around actually in the computers at Leeds. And we routinely process large amounts of ice velocity data to do other work. And so yeah, there's some data that's processed by my colleague Ross. And what got me thinking about this was tidal corrections, which again, thank you Thomas for introducing those, are something that's applied to ice velocity measurements over ice shelves. But what if we sort of flip that logic and say, well, we know what the tidal signal should look like. Can't we use that to detect what's floating and what's not? So again, Thomas introduced this a little bit, so I'll go through it fairly quickly. But where there's vertical motion of the ice and your DEM doesn't account for that, and you assume surface parallel flow, which is what we generally do when we're doing ice velocity measurements, a vertical motion will create an apparent motion in the range direction because of the incidence angle of the sensor. And that might seem like it would be fairly small, but actually a meter of vertical motion at 45 degrees is a meter of horizontal motion. On 6-day pair, that's 60 meters a year. That's quite a big signal. So normally we're correcting for this, but actually, say, this signal can tell us what's floating and what's not. So if we take a time series approach, we can have a little algorithm which I'll describe here. So we feature track our SAR data, we extract the range component, and then we get a time series of tide height corrected for atmospheric pressure. We create a time series of expected vertical displacements where the viewing geometry is fixed for like a SAR frame over time. That's just a linear, the range direction error signal is just a linear function of the tide height, so you don't need to do any more calculations. You can just look at the cross correlation between those two. And that's illustrated by these figures here. So you've got the red cross, which is on floating ice, and the blue cross, which is on grounded ice. And when you plot tide height against displacement anomalies, you can see that the red point has this nice correlation, linear fit with tide height, and the blue doesn't. And when you look at the time series, you can see that even more clearly. So the red time series is the floating point, and the black is the tide. They are almost exactly the same. This is a spot where it works nicely, but you see the principle. And if you've got a lot of data and you've got a big computer, you can do this everywhere, like this on the peninsula. And this is what you get when you calculate the correlation between those two. And this worked a lot better than I expected, so I was very pleased with this. And a little tour of the peninsula. So panel B, that's the sea on Nunataks ice shelf, the remnant of Larsen A and B that's attached to those little volcanic islands. We resolved those really nicely. In the Scar Inlet, the Larsen B remnant, panel C, we can see those pinning points close to the grounding line, and on that western margin where correlation generally is very bad. And Larsen D ice shelf looks great, and on George VI ice shelf, where the tide heights are much lower than the eastern side of the peninsula, the method still works well. We're able to resolve islands, pinning points, etc. And here's a little interferogram to convince you that we are really measuring the right thing. So panel B, there's an interferogram produced by Kai, who's co-author on this paper. The grounding line there has been manually delineated from that interferogram. This is for 2019, so it's concurrent. And then below that in panel D is the tide correlation with an automatically delineated grounding line that we just contour at a threshold of 0.1. We would use 0, but that generally leads to noisy results. You can see that those match really nicely. And when you look at the INSAR coherence, which is another way of seeing that hinge zone, you can see that, here, we are actually picking the inland limit of that hinge zone really nicely. And comparing that to some other data, which has also already been introduced, so thank you. Mojrani produced AI delineated grounding lines for all the Sentinel-1 interferograms in 2018. It's a really great paper. If you haven't read it, I recommend you do. And when we compare our data to this, our data is the white line against the pink lines. We find that, yeah, we're pretty much going down the middle of those automatic grounding line delineations. So a good interpretation of this measurement is we're measuring the average position of point F throughout the period. So just to show you another example, because I can. This is the scar in that ice shelf again, the remnant of Larsen B. That's an interferogram from 2019. Get good coherence on the eastern margin. This hasn't come out that well, actually. But here, and on the western margin, we'd get no coherence where it's fast flowing. And if I plot the grounding line from the figure on the left onto the one on the right, you can see that actually it lines up really nicely. And then to take a more systematic approach, we can look at the large-scale performance, so against the measures Antarctic boundaries grounding line, which is not the most current, but it is the most comprehensive in terms of coverage, and it's widely used in the community. Comparing these 5 regions, we find a mean seaward offset for our data of less than 200 meters against that, which, considering this is not a phase-sensitive measurement, I think that's pretty good. And when we compare that against interferograms that we produced in 2019, we find, so they're produced at the same time as our tidal data, but they're manually delineated by us at Leeds, so it's not entirely independent measurement, but we find that, yeah, roughly agrees at 200 meters of seaward offset for this tidal data. So hopefully I've convinced you that this works and it's useful and that it's pretty good measurement. So what can we use it for? Well, we can look at pinning points as one thing we can do. So around the peninsula, there's quite a lot of pinning points. They're important for ice shelf stability. We can look to see if they've changed. And we find that there's some pinning points that hadn't been mapped before we find. We also find others that disappeared. And then a good example of this as well is on the seal non-attacks. You can see that those pinning points, those islands have shrunk. They've got smaller. That indicates the ice shelf's thinned, which is what you'd expect in that area where the ice shelf's basically stagnant. It's not being fed by anything anymore. And we can also use this to measure grounding line retreat, which is probably the more exciting thing, and produce new measurements where previously the last data was before the collapse of like the Larsen B and A ice shelves, so you consider it to be probably not current, and that's indeed true. So on Hectoria Green Evans Glacier System in Larsen B, we find that the grounding lines retreated by 16 kilometers since 1996, which is the last time-stamped INSAR grounding line available. And a similar story in Larsen A and on Edgeworth Glacier. I've included Crane here as well, because Crane Glacier is quite interesting. Seemed like it may have been retreated and then re-advanced later, which would make sense because it was thickening and slowing in this time. Since these measurements were done, there's been a large loss of sea ice and retreat of glaciers in this area. And our results show that that's largely on floating ice, thanks to these new grounding line measurements. So this is helping us to interpret and understand observations that we've been making on the peninsula. So to kind of sum up, we all agree that grounding lines are an essential thing to monitor, and existing methods do a great job generally. There are a few places where it's more challenging and there are still problems, and the peninsula is an example of that. The peninsula in many ways is the awkward bit of Antarctica to study, I think. At least that's my experience. And we produced a grounding line data set for the peninsula from 2019 to 20. Hopefully that will be available soon when this work is available as a preprint, hopefully sometime this year. And we've already started to use these grounding line data sets we produced from this work in other studies. So colleague Tristan had a preprint released a few weeks ago, last week, 2 weeks ago, recently, about the changes in the Larsen B inlet after that loss of sea ice. And we use this data set to initialize ice flow model of those glaciers. So we're already using this data to help us understand the process that have happened in the peninsula. So I'll just leave it there with a little summary. I think that monitoring grounding lines is an achievable goal, and it's something that is best done with a combination of methods. So INSAR would make up the bulk, but I think smaller methods like this that can address smaller issues with specific areas are still really useful. And we can also reduce the uncertainty in measurements by measuring the same thing with multiple techniques. And this method works best with 6-day repeats as well, because the tide signal is greater compared to the ice velocity. So yeah, if we could have 6-day repeats back, that would be grand. And then we could produce a new version of this and look at change. So yeah, thank you very much. I'm happy to take any questions.
Okay, thanks, Ben. There is time for one question.
Did you say how many? Thanks. Did you say how many data sets you need to derive this correlation coefficient?
Yeah, so this map was made with 2 years worth of Sentinel-1 acquisitions. It does work with 1 year as well, and generally that's the sort of time period. So these are done with, we use only the wintertime acquisitions because there's no surface melt, because the surface melt can induce a vertical change in scattering horizon.
So number of acquisitions?
Yeah, 20 to 30. Yeah, we use 6 and 12 day pairs, say about 20, 30, 6 months worth of Sentinel-1.
Thank you very much.
Sorry.
I have also one quick question. Did you test this also with the 12 days repeat? And does it work there? Because you have first less acquisitions during the winter period?
Yes.
And of course a bigger time difference.
Yeah, it doesn't work as well with 12-day pairs. The performance suffers particularly on smaller glaciers. So you still get results on, say, the ice shelves, but not sort of small areas where generally we're targeting anyway that we can't get coherence.
And are you planning to apply this for the complete Antarctica at the end, or?
Personally, not particularly soon because I'm trying to finish my PhD.
So your PhD is done.
Yeah, but the peninsula in many ways is the best place to do this because the tide amplitudes are large. So other regions of Antarctica, like the Amazon Sea, have much smaller tides, so you probably need a longer time series to get enough large differential tides to get a good result. I will make the code for this available when it is published as well, so other people could use it. I think that's a realistic goal I'd like to try, but it's not on my horizon currently.
Thanks, yes.
Fantastic. Well, I think we have to move on in the interest of time, so I can see Marcus looking at angrily from the back of the room. But thanks very much, Ben, for a brilliant talk. So next up, we've got a presentation from Andrea Puella from DLR, who's going to be presenting on supervised learning for tracking inland glacier flows using TOPS data. So thank you very much.
Just give me
Take it away.
1 second to, oops. Okay. Okay, thank you for the introduction. Good morning. In this presentation, I will show you a convolutional neural network for tracking inland glacier flows using a single interferometric pair of Sentinel-1 TOPS data. First of all, I want to thank my colleague at DLR, Claire Renaud and Paul Prats, and Francesco Paolo Siga from the University of the Bundeswehr. Okay, as the first slide suggests, I will start with an introduction. What is the INSAR, TOPS, and then I will go through the main problem, that is the phase jump. And I will show you how our proposed methodology, that is considering a supervised convolutional neural network, and experimental results from using synthetic data and real data. So finally, conclusion and the outlook. So what is the INSAR? Basically, we have a repeat pass acquisition mode. We are acquiring at different time over the same area, and what is of interest for us is that if we have within this time frame a change in the topography, we can retrieve let's say an interferogram like this that is quite interesting, because by looking at the fringes we can also extract some measurement like the amount of deformation. Yeah, the main message is that the D-INSAR is sensitive to the line of sight. And with StripMap is quite easy to extract this information. But what happens when we have more complicated acquisition mode, like TOPS? So TOPS, just briefly, is an advanced scan-search technique used in most modern search systems such as Sentinel-1. It has the advantage of increasing the coverage at the expense of the azimuth resolution, and as this picture suggests, you can see that we are switching the antenna between the subshot, and we are acquiring a portion of this subshot that are called bursts, using within the burst an electronic antenna beam steering. That is the main responsible of the phase jumps. First, I want to what's happening? I don't know why the presentation is freeze. Okay, yeah. First, yes, I want to see the problem for an image parameter, the Doppler centroid. So basically, this antenna steering, let's say, is constant along azimuth, and it generates a linear variation along azimuth that can be expressed by these formulas. This is the Doppler centroid frequency shift, and you can see here a graph that is showing the main variation along variation along azimuth. For us, it's important to extract from the framework of convolutional neural network. It's important to extract a feature, and how can we do it? We can look at the extract a 2D map that is taking into account also the range variation that is always possible to extract from the annotation parameter of Sentinel-1. So these are the features that I will show you also in our network. And basically, you can see I'm focusing the attention on a single subshot, and we have this red, white, and blue color map that is showing us that the main variation is along azimuth, yes, in our framework, what is important to underline is that we are mosaicing the burst, and this burst and the result will be a subshot with a discontinuity in the overlap area. And I want to go ahead and show you an example of how the phase should look like. So let's suppose I'm doing a simulation. Let's suppose that the deformation is constant in both directions. I put 50 centimeters of constant deformation. The along track motion is still constant, but the interferometric phase that is here on the right is presents some jumps, and these jumps are associated to the adjacent burst. So in this case, we have 4 bursts and 3 phase jumps. And what we can say is that we would like to have a zero Doppler phase, so a contribution that has no jumps. And so we can model the problem as, let's say, model the interferometric phase as the rapid sum of these 2 contributions, the long track phase associated with the motion and the zero Doppler phase. So phase jumps between adjacent bursts basically potentially interfere with the phase unwrapping step and do not allow the Doppler displacement estimation. How can we solve the problem? First of all, we have to invert the deformation from the phase differences in the overlap areas. And I show you, let's say, our suggestion. So basically, we are fixing an interferometric phase mixing model, which consists of 2 SLCs described as follows. So we are synthesizing the primary as the product of the noise-free amplitude plus the Gaussian, the circular Gaussian noise, and while the secondary as you can see, is a little bit more complex because it has inside some parameters that they have to induce the deformation, the desired coherence rho, and the theoretical phase phi tau. Phi tau can be seen also as a noise-free interferometric phase, something like the interferometric phase I was showing in that simulation data. Indeed, it is the rapid sum of these 2 phase contribution, which can be always extracted if we know the deformation. So, given a deformation, we can use always these geometrical properties. And this geometrical system, so the incidence angle and the north angle have an impact. And this brings us to our idea of defining input and output for our network. So we will start from the interferometric phase. And given this, we will try to solve simultaneously two problems. The phase source separation, so try to split in two-phase contribution at zero Doppler and the along track, and at the same time give an estimate of the along track motion. Okay, I want to show you first, let's say, how a synthetic dataset can be generated, because we have first to do a training. And to do it properly, we decided to take as input the deformation retrieved within the Promise program. So this is these are basically a freely available data set. We are talking about annual, every year the University of Denmark is providing these winter velocity maps with a nominal resolution of 500 meters, and they are based on the Sentinel-1 SARPEC scatter. They are doing a sort of cross correlation, if I'm saying not bad, this thing. And this is the main synthetic data set. Basically, as you can see, we did a backgeocoding on some footprint. So a backgeocoding of this deformation of this SLC acquisition. We selected 9 out of 10 of them for the training. And we added also additional information just for data augmentation. We used the deformation from a mathematical model, this Okada model that is used more for solid earth, but can generalize more from the point of view of the phase jumps the problem. Okay, another point that is interesting is how we treat the patches. So by using this mixing model, we are extracting the subshot after the bursting. We want to extract the patches. The solution we suggest is to take, let's say, patches whose size is bigger than the azimuth. The azimuth size of the burst after multi-looking, and they have to be centered and mid-overlap, because in this way we can exploit these inputs. So first, the inputs will be let's say the real and imaginary part of the phasor associated with the interferometric phase. Rho is the coherence, and the Doppler centroid frequency, okay, is this one at mid-overlap, so we are looking at the patch. The output instead will be 5, because, okay, we are working, okay, with a long track motion, and at the same time we are let's say we are going to extract real and imaginary part of the two components that can always be reconstructed afterwards. This is the convolutional neural network that we are suggesting. Just I want to spend a few words. It's a modified unit. Basically, you see the encoder and the decoder. But what is changing is basically we are adding let's say adding another branch. So we are at this in this bridge layer we have 2 branches. The branch on top is responsible of the estimation of the along track and zero Doppler phases, while the branch on the bottom is dedicated for the sole along track motion. What is important of this network is that it is, let's say, it goes toward the concept of the multitask learning. So basically, we are trying to estimate simultaneously output parameters that are interconnected among them. And I can show you, let's say, the interconnection. just briefly, okay, nothing so special. The zero Doppler phase is the wrap difference of the interferometric phase and the along track phase. The along track phase can be retrieved from the along track motion, and we can also fix some regularization, like the zero Doppler phase must be continuous. Since we are working with the real and imaginary part, the phasor has to be unitary, and the along track phase has to be very similar to the phase reconstructed from the estimated along track motion. Okay, so I have 3 slides just to show you the results. Okay, first on synthetic data. We left out a footprint just for doing our analysis, this footprint number 8. And basically what we did, we induced the deformation in this mixing model, this promised deformation. So basically we are retrieving the subsort, and in this table, I am basically splitting the patches in different cases. So we have the case A, that is low density fringes, B medium, and C high. And I can show you here the RMSE in terms of average and standard deviation. What I can briefly comment is that in both the cases you see that, especially with the phases, we have one order of magnitude lower than the average, and this is a good sign of the let's say of the reliability of our network, and then. Okay, but you have the same lower values for the long track deformation. I show you an example just to give you a feeling on the error. So both for the phases we have error lower than pi over 50. And for the long track motion, values that are lower than 0.03 meters. And now I want to show you a result on a real data. So we took a pair of acquisition with a time span of 12 days over the same footprint number 8 that I was mentioning before. And we took this area because we saw that the ionospheric effect was less dominant. And here I'm trying to compare with the state-of-the-art algorithm our solution. I just briefly comment. Yes, okay. In the first column you can find the output, the input. In the second one, the speckle tracking, the result of speckle tracking. Basically, we are applying a refinement to the co-registration using offset estimated from the incoherent cross-correlation technique plus the spatial diversity. In general, the advantages are that the solution it's a solution for extremely large displacement, but it penalizes small displacement that are usually confused with noise. And then in this second state-of-the-art methodology, I want to show you the result that we get by observing in another way the problem that consists on looking at the overlap and extracting the differential interferometric phase. And since we know that there is a direct connection with the along track motion, let's say apply an inpainting that basically is filling the huge gaps that we have among the bursts. The advantages in this case are for sure the measured displacement overlap that is accurate, but we have problems because we have to use a 2D phase unwrapping, which in general is quite tricky. Overlap regions are very small with respect to the burst, and there is also a high computational complexity. I want to just focus the attention on these patches and show you how our algorithm is solving some also tricky problems, especially here where there is a glacial flow. I'm just showing the zero Doppler here phase, and here I want to show you the final results also. I hope you can see also in the bottom the name of the variables. You can see that on the left the inputs that are the coherence and the interferometric phase. On the right the zero Doppler and the long track phases and the long track deformation. Just one small comment. If you look at I'm showing you the three subsets. In the first row, you can see the first subset, and the first subset we have a low coherence. Our algorithm is also doing denoising, and you can see it on the zero Doppler phase, and the algorithm is also able to, so it's with respect to the long track motion, we can say that the algorithm is able to estimate the value at mid-overlap at the expense of the mid-burst, where we have also a zero Doppler situation, if you think about the Doppler centroid frequency. Conclusion. So basically, we propose a methodology for phasor separation. We provide a proxy for surface displacement estimation that is superior to the state of the art, and we are able to estimate glacier inland flow where both state-of-the-art algorithm cannot provide a solution. And these are the outlook. So thanks for your attention.
Fantastic. Thanks so much for that presentation. Have we got a question from the audience at all? Yeah. Andreas.
Thank you for a nice presentation. Did you use a velocity map for the co-registration before perform the interferograms?
You mean, okay, basically, okay, here, I think this slide, I guess you are, okay, the promise, yes, is providing clearly the ice velocity map. I am generating the associated deformation by applying there is a, let's say, the revisit time that we have to take into account of Sentinel-1, and I am just multiplied by revisit time, and then with this deformation, I am doing the back decoding to the SLC, just to have let's say the parameters that are consistent with at the SLC level.
But are you also co-registering using this map, or is it just standard?
No, this map is a geocoded product.
Yeah.
So and this so
it's just.
The question is if you use the velocity data in order to co-register.
No.
Because then you get rid of a lot of the phase jumps. If you use an average velocity map for the co-registration, then you can reduce the phase jumps already at the processing stage.
Well, in this.
Okay.
Well, in this case, I'm trying to don't be to be independent from the real data. I want to generate some synthetic data that can be used also in different areas. This is the idea behind. So that's why I was not using this velocity.
Okay, thank you.
Okay, then I want to thank you for this very interesting presentation, and we go on with the last talk of this morning session. It is on the geodetic mass balance of glaciers and ice caps from tandem X in northern high latitudes, and it will be given by Philipp Malz from University of Erlangen in Nuremberg.
Okay, thank you for the introduction. Hi, I'm here to talk also on behalf of my group about geodetic mass balance of glaciers and ice caps in northern high latitudes. A little bit of study design explanation. We are actually doing an application of INSA-derived DEMs. To be more precise, we are differentiating tandem X DM products, not speaking of the global DMs, published as you know, but we are taking the co-SSC that we can extract from the online catalog, and we do the interferometry processing ourselves. So that's the checkbox for being here and talking at an interferometry conference. And we attempt to cover all glaciated area of our study sites at least twice, so that we have a surface elevation change rate that we can see between these two periods of acquisition. And from that, we eventually then derive mass change with a mass conversion. Speaking of study sites, on the upper panel you see the Randolph Glacier inventory regions 1 to 10 with labels, which are actually what we are looking at today, or more precisely parts of them, because as the abstract also indicated, it is a little bit of a work in progress presentation. So on the lower panel you can see where we managed to find overlapping footprints on glaciated area to compare, so to extract surface elevation change rates that can be converted to mass change. And it's not completely updated, so Svalbard is completely covered, and the Arctic Canada North seems a little bit less covered than it is actually now, but Greenland is still lacking a lot of data, so I will be not talking about the Greenland periphery today, but for the other ones I will show you some examples of results, leaving out Scandinavia because it's too widespread and actually too small. No offense to Scandinavians at that point. So a little bit about timing here. Tandem X is basically a SAR interferometer with the mission goal to derive global DMs, as I already mentioned, and the period of acquisition is more or less covered in this center panel by these red dashed rectangles. So you could think, why is this so large areas of time to acquire a global DM? Well, there is an 11-day repeat cycle of this 10 twin satellite, but mission design does not include continuous acquisition. So it took quite a time to cover the global terrestrial area, and for us that means we have to look in the catalog what is actually there and select very precisely what we are taking for our INSA DM production, and what the main periods of our chosen scenes is now covered or depicted in the filled red rectangles in the center panel. So we had about delta T of 5 years, which we tried to differentiate between, and yeah, we tried where possible to keep a full glaciological year covered to avoid seasonal distance. You will see that it is not always possible, which is also seen on the right panel. There you have in cyan a long track concatenated footprints where you of course have the same acquisition date because it's one continuous acquisition, but then a cross track you see in this grayscale that it's not completely possible that when you merge these DMs to a mosaic that it's all from the same acquisition date. So this is now just qualitatively showing that this might differ, and you will see what that implies. But first of all, let's start with a processing method from the very beginning. So at first we have about 11,000 image pairs from the archive, which we process and sort, as I said, in a long track direction to longer strips that is more easily to process for us. And then we do the interferometry processing, which we use gamma software for. It's quite a standard differential interferometry, but we re-add the terrain phase, so we get full DM products, which we later on correct to the reference DEM with a Newton cap corrections. It's a very common co-registration method, and to compensate for shifts in X, Y, and Z direction. And after that, we have this kind of strip products that you saw in the slide before, which we are able to mosaic, and we have a mosaicing algorithm that sorts the dating, and I can elaborate on that a little bit later if you want to in the question part. So once we have reached level 3 here of the processing, you should have a mosaic of DEM, and whenever you have 2 overlapping fitting mosaics of DEMs, and you know the acquisition date, as I showed you before, respective to that, you can derive elevation change data sets, which is what you see in the center. Also here, only qualitatively, you will see a lot more of them later on. And with these mapped results, then we go into a more numeric analysis. So we do a gap filling where scenes could not be fully acquired in the overlapping areas. So hypsometric interpolation of gaps in there, and then we do a mask conversion with 2 scenarios. I will present the results of the conversion with the 850 kilograms per cubic meter for transferring to gigatons of mass loss per year. In the area surrounding glaciated area, we do also an uncertainty assessment to see the systematic accuracy of the height measurement, and we also add uncertainty estimation of the propagation of the signal into upper reaches where snow and ice might be not fully compacted or not wet, because we are talking of radar satellites, of course. And that is at the very moment from the median elevation to the highest elevation, a linear interpolation of 1 to 5 meters penetration signal. Okay, so that is then when we reach level 5, the end of level 4, that we have this one-line result of terabytes of input. So that is why I want to also mention that with the scalability of the code, we also had the opportunity to use our high-performance cluster, and I want to acknowledge that. So speaking of results, I showed you a dH by dt map before, and this is now a region-wide dH by dt map, and we are starting in one of the northernmost regions here, which is now Arctic Canada North. So you have Ellesmere Island and Baffin Bay to west. I had to split into parts because I wanted to show you a really large depiction of that. What you can see is that the color bar, I will leave that constant from -3 to +3 meters of elevation change per year, is here not used very much to its extremes, so very large parts of more or less neutral signal, but you see a slight tendency to negative change as well. What you see as well is that in some areas, which I don't want to just go over, you still see that the sorting algorithm is not fully sorted out, so there needs to be some manual preparing of the results afterwards as well. As I told you, this is just work in progress results. But as for the mean elevation change per hypsometric bin, we do a filtering of 2%, 2 percentile, like upper and lower 2 percentile. I'm quite convinced that also these mosaics that I show you are representative enough to give you mean elevation changes per hypsometric bin, which is plotted here. In blue, you see the, how much area per hypsometric bin is available. They go in 50 meters from a very zero sea level to up to 2,000 meters here. And in the overall mean of the area, you see that we have about minus 30 centimeters per year of elevation change with a large area of over 100,000 kilometers square, result to 31.22 gigatons mass loss per year in Arctic Canada North. Going on to the southern part of Arctic Canada, we have now Baffin Island with Baffin Bay to the northwest, as you also see in the overview map, and the picture is a little bit different, so you see a lot more reddish tones here. And what you also see is that now we see some not so seamless mosaic effects, which are due to not being able to really acquire these large parts of Canada in all one season and 1 year. So that results to this overview of result figures and hypsometric bin. You see in the distribution of the change rate that it is significantly more negative, which brings us to about 90 centimeters per year in the mean over all the area, and with less than half of the square kilometers, we also get like about 30 gigatons of mass loss per year in Arctic Canada South. Going on to Iceland, so the other side of Greenland, Iceland has this particular distribution of glaciers on these ice caps on craters, where you see that the elevation change signal, particularly here, is very much more negative to the margins of these ice caps. So you see that in the hypsometric distribution that they are very large, the mass losses that we see here, and they also exceed the color bar that I put here. So they are reaching up to 5 to 6 meters on the margins, and even on the outlet glaciers, they reach up to minus 10 meters per year. Overall, for Iceland, a little bit of a smaller region, as you see. We get minus 6.3 gigatons of mass loss. And one of the most promising results so far, I would say, we go to Svalbard. Most promising because the mosaic looks very good, and it also depicts the very strong mass loss. So we are again going up to the very northern latitudes here. But you see in southern Spitzbergen, very strong reddish tones and very strong signals, which in this case, I have to admit, also come from surge activities. A surge is when a glacier, as you might all know, since you're in an ice session, accelerates abnormally and produces a bulb, which is transported ice downstream. And in parts of these elevation change field, you see this bulb appearing in blue down valley, but in other parts, it's not covered by the Reyndorf glacier inventory in this case, so we might be missing a little bit of, or we might overestimate the signal here a little bit. Yeah, I also want to comment that the ice caps Ost and Westfauna are more or less stable, apart from that one surge that is also here depicted in Ostfauna. And you can also see that we're not fully done with coverage here. And some parts are still missing. So, and that brings me to the last region I want to show you results for as pictures or as maps, which is Alaska. And here I want to mention that it's very unfortunate when we miss a lot of signal, because we are missing the coverage of outlet glaciers, which here refers to Malaspina Glacier completely, which would be a large part of the signal of mass loss in Alaska here. Bering Glacier and Columbia Glacier are covered, which are also contributing really strongly with loss rates of about 10 meters on Bering Glacier, and as I remember correctly, I didn't put it here, it's still about 8 meters per year on Columbia Glacier as well. And you see a lot of surge activity going on here, and it's a pity that we have not fully covered this area because it's one of the largest contributors. So when I go on to the summing up of the results, we are missing out Alaska here, and I also spared Western Canada, US, because we are also missing parts of the more southern region, which would not be a fully representative signal then here. So summing up the regions I mentioned and adding Scandinavia, which we also analyzed but not included as a DH/DT map, and publication from a colleague of mine, about the Russian Arctic, and summing all the mass change rates together, we end up at 110 gigatons mass loss per year for these 1, 2, 3, 4, 5, 6 regions, which is not 10, obviously. So that is still, there is still some work going on, but we can conclude from here that our DEMs derived from those COSA, SSC, from the archive are really applicable for this dam differencing on glaciers, and the mission properties do not really allow to make complete year consistent and season consistent mosaics, but when we sort them out very carefully, then those elevation change maps can successfully be performed, and such can the mass loss rates be extracted. Yeah, and the rest I already told you, and with that I want to thank you for the attention, and I'm ready for questions.
Fantastic, thanks very much. Really nice to see the surface elevation change in such high resolution there on those very small glaciers. Have we got any questions from the audience? Lucas.
Thanks for the nice talk. I was wondering on the scene selection strategy and the mosaicing priorities that you applied, because as far as I know in the community, there are two ways to approach this. Like one, to go for the end of ablation season to have limited penetration signals of the scenes, or like to stay in the same season, like use winter acquisitions, which is from a source perspective, like you have better backscattering, you have nicer DMs. Did you favor one over the other in your mosaicing?
So maybe you can repeat parts of the parts I didn't get. I can answer first, and then you just add what I didn't answer. So in our sorting algorithm, we just first of all look where the main part of our acquisitions come from in the first acquisition period, and then we try to make a fit to the second acquisition period as good as possible to a central year and to a season. So season offset means in our case that we are defining a central acquisition date from which plus minus 40 days we are allowing acquisitions to be mosaiced, and the rest is first of all rejected to a lower priority. Then we are giving 1 year plus and minus off in the same season with central acquisition date, and then again, if that doesn't cover all of the area, we add all of the rejected DMs. So basically that works quite okay, but unfortunately we cannot always stay in the same central acquisition date for all of these regions. So it works quite well for some of them, but as you might have seen in the in this table, there is also a DT median given, and so for Svalbard, for example, worked quite well. For Iceland, we are also confident, but yeah, Scandinavia, for example, seems to be a little bit off-season for the most part, and that is something we can care for and try to find other acquisitions, but as I mentioned at the beginning, we have to rely on the catalog and take what's there. So in the end, we can only then do a seasonal correction, which is still work in progress, but we cannot change the acquisitions anymore.
Okay, thanks.
Can I ask one final question, if I'm allowed? Very good, and I haven't asked any questions so far, I think. What do you think the largest uncertainty in your data set is in the final result? And I'm just kind of thinking about, going back to what Irina said earlier about penetration effects. Do you think that that's been a factor? There's lots of melt in the glaciers and ice caps.
Yeah, thank you very much for that question. It's a very good question, and you're completely right. So the largest factor indeed of our uncertainty at the moment is that uncertainty we add for radar penetration of the signal. It's, yeah, at least, I mean, it's still, since we do a hypsometric linear interpolation of that thing, it depends on the distribution of the glacier area as well. And so that's also, when we look at this table that is now presented here, where we have the largest uncertainty parts, is also where the largest ice masses are in the accumulation zone. So that is then about, yeah, can be up to 80% of.
I have an add-on to this question. Do you account somehow for the surface conditions when the Tandem X data are required? So wet versus dry, because you're covering quite a lot of glaciers in different environments. So the penetration is a problem, of course, when you have dry conditions. But sometimes you might have also surface melt in lower parts. So do you take this into account? Or?
So thank you again for the question. It's also a very good question. In the publication seen on the left, my colleague Christian Sommer did something like that when he examined the backscatter intensity of the different acquisitions in acquisitions that were off-season. So we tried to account for that. So far, we also produce all the backscatter intensity images for all the scenes that we derived the DMs for, but it's not fully implemented that we also look into those for corrections, but can be done.
And maybe, sorry for this, but what are the plans once Tandem X is not providing any data anymore? So do you have a kind of backup strategy for continuing this work?
We don't, but I'm happy for suggestions. That's why we're here as well. Yeah, of course, it would be great to have a continuity mission in X-band acquiring, but yeah, there's not so much on the horizon. So
maybe I reformulate. Do you think that Harmony could extend this work, what you're doing?
I'm not sure yet, but so we didn't look into that. Maybe that's the correct answer of the question, not so far. Yeah.
Well, it's turning into a PhD Viva rather than a Q&A session, so let's leave it there. But thank you so much for all your answers to the questions. Fortunately, ESA are listening. I can see Malcolm hearing that we need more X-band SAR missions. Irina's there. We've got multiple space agencies that I'm sure will be wanting to launch once, and certainly Calvel campaigns to account for these differences in both the DHDT and the velocity is important. So we're going to wrap up the session now, as it's time for the lunch break.
Yes, I have an announcement to make. So the gala dinner on Thursday, so please, if you're registered, please pay your bills by tomorrow, but better if you do it today. And I can really recommend this venue. I mean, I made a mistake in my opening address. It's this space literally between rugby stadium and cricket stadium. It's superb. It's really one of a kind, so I can highly recommend the dinner. So if you have not considered it yet, please do so. All right?
Fantastic. And also just to say before we go, don't want to hold you for too much longer, but we've got the ice and snow roundtable discussion session at the end of the next session. So the next ice and snow is going to be in this same auditorium, so come back here after lunch. And right at the end of it, we're going to have all the chairs come up for the roundtable discussion. And we've drafted some seed questions, as we always do for these ESA conferences. And just to give you a little bit of a taster, so you've got something to think about over the lunch break. Some of these questions are, what are the most important science things that should be addressed using SAR data in the polar and cryosphere regions? What are our gaps in monitoring parameters that we need for ice sheets, glaciers, and snow? How can we coordinate and optimize SAR acquisition strategies over ice sheets? Thinking about Sentinel-1, NISAR, SARCOM, ROSEL, etc., and what are our priority regions, and more. So if those questions haven't sort of got you excited, we've got more in the list, and we're really excited to hear any other thoughts that you've got. We will be taking notes and these recommendations will go to ESA, and they want to hear what we have to say. So thank you very much, everyone.